So today what I want to talk about is really kind of a summary of a lot of the research work I've been working on since my PhD. So I finished my PhD in 2016, getting to be almost going on 10 years now. And as a side project in that PhD, I did a project in Bermuda that I'll show you in a while, where we looked at the climate of Bermuda in the past. And the way we did that was with things like this. You're looking at a glycimerous shell here that's sticking out of some rock that basically we do a lot of geochemistry on. So I will warn you in advance. We are going to talk a little bit geochemistry today, though I'll try to keep that as um, sort of superficial as possible. I also freely admit that probably many of you know more about the actual fossil species I'm going to talk about today than I do. So I'm very much more of a geochemist and sedimentologist than someone who really knows their invertebrate paleontology. I tend to pick up what I have to do the work that I'm going to describe here. Um, so to just start with, it's always good to just, oops, okay. Always good to just start with who's talking to you right now. So that's me. There's a picture of me in Bermuda looking at shells. So as I said, come from a background in carbonate sedimentology and geochemistry. So I'm in a geology department now, actually also in an environmental science department here. And so a lot of my work has been focused on climate and some of it not so much focused on climate, more on the formation of things like limestones and dolomites across geologic time. I am at a undergraduate only institution, so a lot of my work is with students. I'm going to feature some of those students briefly here, but pretty much everything you're going to see today was a student project of some sort on some level. That picture in the top right is um, basically to represent the geochemistry, lots of liquid nitrogen and things moving around in vacuum tubes there to do some of the actual analyses that I'm going to show you the results from. And plenty of people have not heard of Grand Valley, so I'll put it on the map there. Uh, it's here in West Michigan, so I live in Grand Rapids. Uh, I went to grad school. A lot of my grad school was at the University of Michigan. I also got a master's degree over in North Carolina, I guess slightly closer to you all. And that's actually where a lot of my work on the East Coast started. So the first kind of data set I'll talk about today is actually all along the East Coast, sort of jumping over where you all are, but certainly in your neck of the woods more than over here. As I tell our students in our classes at Grand Valley, like they've sort of picked the worst place in the country to study geology if they want to look at bedrock geology, because all we have here is glacial garbage, as we colloquially call it, right? We only have all of our bedrock is buried under about 200 to 500 feet of glacial sediment. So if we want to see bedrock, if we want to go find ancient fossils, we have to drive at least a few hours, drive to places like Kentucky to go see those things. All right, so what am I actually getting into today? We'll talk very sort of briefly about the main time period. Everything I'm going to talk about today is from the same time period. That time period is going to be the last interglacial, also just called the last time it was about as warm as it is today. And I'm going to give you three projects from that time interval. So we're going to talk about the entire East Coast kind of as one project that's pretty much in the works, but I have enough data to kind of show you the overview there. And then we're going to talk about the Bahamas. Kind of got an open and shut story that was just published this year on the Bahamas, and then ongoing work in Bermuda. We've published, I and other folks in what I would call my research group, so some colleagues at the University of Michigan, um, have published three papers now on climate in Bermuda, and we're working on a fourth one that kind of brings that all together. So I'll kind of give you some data that's published, but also some ideas about where that's going in the relatively near future. All right, so why would we care about the last interglacial? So we live in an interglacial right now, right? Everyone here, I'm sure, is familiar with the concept of an ice age and glacial intervals. So it turns out there's not just one ice age, there are many ice ages going back in time. Over the last million years, there was, something like 5 to 6 ice ages. So in between those ice ages or glacial intervals, we have warmer times. And to make a very long story short, these warm and cold times are driven First by orbital cycles. So there are changes in how the Earth is actually moving around the sun, how it wobbles in that orbit, how circular that orbit is. And that drives changes in kind of where sunlight's reaching the planet and sets off climate feedbacks that then can warm or cool the planet in different ways. Now, exactly how all that works is sort of beyond the scope of what I can get into here. But what I can say for sure is that the last time this happened, the world was a little bit warmer than it is now. And when I say now, what I actually mean is pre-industrial, right? So, picking a climate state that is now is a little bit tricky since we are in a rapidly changing climate state right now. But, especially when we're talking about paleoclimatology, the study of ancient climates, we're talking about in relation to something like 1800s climate, right? Before we start to dramatically increase temperatures. And so relative to pre-industrial, we think the last interglacial globally was maybe a degree and a half warmer than today. And if you're someone who follows climate science to some degree, you know that, there's talk about whether we can keep global warming to 1.5 degrees or 2 degrees or 3 degrees and so on. So the last interglacial has been put forward as an analog of here's what the world looks like if you sort of lock it in at 1.5 degrees Celsius warmer than today. Now, there are some caveats to that, including that the poles look like they were quite a bit warmer than today during the last interglacial. And the tropics, so these blue dots here, let me see if I can point at this. Can you all see this laser pointer? Is that coming through?
Yes.
All right,
Yes, we can
great,
see it.
great. So these blue dots sort of in the equatorial regions are kind of showing us that the tropics were actually maybe a degree-ish colder than now, and the poles were quite a bit warmer. And if you average all of that out, you get to this 1.5 degree number. So nobody studying the last interglacial says this is a perfect analog for exactly where climate is going in the next 100 years, but it's at least a state that we can kind of study and compare against. It is a world where the climate is a little bit warmer than pre-industrial. Um, so this is a map of basically every piece of work ever done on the last interglacial. Most of these data are going to be from ocean cores. So taking a big ship like the JOIDES Resolution, drilling down into muds at the bottom of the ocean, pulling back out that mud, which also includes tiny little microscopic shells like foraminifera, and looking at the geochemistry of those shells and the species types of those shells and so on. Some of this stuff is from pollen. So a lot of the dots on land are going to be from pollen data. So in other words, all the dots you see on this map are not the exact same approach that I'm going to be using here. There also is at the global scale, this coverage maybe looks pretty good, but once you start thinking about regional scales even a little bit, there start to be really massive gaps in this data. For example, the part of the United States where about 2/3 of the country lives, right? So we have essentially no data from the eastern United States during the last interglacial. We have no data about what this globally warmer climate state actually means on a regional basis. And to sort of simplify this a little bit, we can also just think of the last interglacial as a warm time when sea levels were higher. This is just a easy visual to show that. If you went to Florida in the last interglacial, where you would find your beach resorts would be very, very different because all of the beach resorts you've ever been to in Florida would have been underwater in the last interglacial. Certainly, this is true for lots of places up and down the Atlantic coast as well, but easier to find a map of Florida, so here it is. So of note, during the last interglacial, the Greenland ice sheet melted considerably, and we know a chunk of the West Antarctic ice sheet melted considerably. So sea levels during the last interglacial peaked at about 9 meters above today. So it's argued this number is argued about, so don't hold me to that completely, but let's call it 6 to 9 meters above today. So we're talking 25 feet in that sort of ballpark. 25 feet of sea level rise is a vast amount if we're talking about coastal areas today. And so it's also interesting from that standpoint. All right, so that's the last interglacial. What are we going to use to actually study the last interglacial? My toolkit is looking at the geochemistry of carbonates. So carbonates include things like coral reefs, limestones, dolomites, fossil shells, which I'll mostly talk about today, or living shells. It's also tums. If you've ever chomped on a tums, you were chomping on calcium carbonate, also known as limestone. So that is the stuff we're talking about. And that mineral, usually calcite, also the mineral aragonite, has to form in water. It's something that precipitates out of water. And so when that happens, when a actual crystal of calcite that's making a shell or making a coral or just making algal mud at the bottom of the ocean, when that actually forms, it's going to record the geochemistry of its environment sort of at that instant. It's going to the actual chemistry of that carbonate will reflect the temperature that it's forming at, and it will reflect the chemistry of the water that it was actually growing in. So, for example, a carbonate grown in Lake Michigan, freshwater, near me, will look very different, chemically speaking, to a carbonate grown in the Atlantic Ocean near all of you, even if that's happening at about the same temperature. Like the chemistry will look different. And by chemistry, I am talking about isotopic chemistry. So literally how heavy the oxygen or hydrogen in that water is, or in the case of carbonate, how heavy the oxygen is, which the hydrogen doesn't come along for the ride. So for the most part, when we're talking about the geochemistry of carbonate, at least in this talk, what I'm talking about is that, especially that oxygen in the carbonate. We can actually measure how heavy or light it is, and how heavy or light it is really depends on the water it came from and the temperature that it formed at. And so those types of measurements that I'm describing, looking at the isotopic chemistry of an oxygen in carbonate, depending on your background, might sound, pretty advanced or specialized, but it's something that's actually become quite routine. It's something that's been measured for 70 or 80 years at this point. And so that the main way that's been done is something called delta 18O. If you're familiar with this, you're very familiar with the concept of delta 18O. This is basically a ratio of oxygen isotopes. And this is almost the only time I'm going to try to get into the details of this. If you're interested in this, if you have questions about it, I'm happy to take those or refer you to other sources also. But I'm going to just kind of touch on it here. I'll also say that actually most of the results I'm showing here are a sort of next level and a more advanced way to look at the isotopic chemistry of a carbonate. Most of the data I'm showing you here today is based on clumped isotopes, which are a measure of that oxygen and that carbon. So in the carbonate anion, so that CO3 has oxygen and carbon in it. Very long story short, how heavy those oxygen and carbons are is a direct function of temperature. So we can really, at the end of the day, what all this means is we can walk up to a chunk of limestone or a fossil shell, we can bring it to the lab, we can do some fancy geochemistry on it, and we can get a single number out that is in degrees Celsius, which is what the temperature of formation actually was. And so that, of course, can then tell you something about climate. If I measure carbonate from a warm place or a cold place and I get something, you know, warm or cold, that's or different from expectations, then we start learning something about what the climate of the past was like. Okay. So that's your crash course in isotopic chemistry, at least for tonight. We won't go any farther than that for now. Uh, what I want to get into is the first main project here on the East Coast of the United States. So our goal, I should say actually at the beginning, the three projects I'm going to show here today are all intertwined. They didn't actually happen in the order I'm showing you here. In fact, the Bermuda project sort of started first, and then we did this one, and then the Bahamas one was sort of an offshoot of that. So they're all intertwined. Each has sort of like, lended information to others, but we're going to pick a starting point. So we're picking here. Here's a photograph from a 91-year-old paper by Richards, 1936. This is a bluff in South Carolina. So Charles, as it says, Young's Island, Charleston County, South Carolina. Um, we started this project in basically the Myrtle Beach area. So if you've been to the Myrtle Beach area, you know there is, well, all along the coast, but including Myrtle Beach, there is a intercoastal waterway there. And in Myrtle Beach in particular, the intercoastal waterway was dug through last interglacial age deposits. Now those deposits were not described in great detail in really the last 20 or 30 years. So I'm showing this image because this is some of the material we actually had to work with. We kind of had some guesses about where to go. And fortunately, we had some awesome collaborators, including a guy by the name of Will Dorr down at the South Carolina Geological Survey. It really helped us a lot in actually finding places to go. Because it turns out every time a hurricane comes through, there are new and different outcrops in the intercoastal, and some of the old outcrops no longer exist. And so we had to do some real sedimentological and geologic field work. There's me uh, investigating these shell beds here. And hopefully over Zoom you can at least see there's lots of sort of white flecks in this strata. Those are all fossil shells sort of falling out. And this is, again, geologically speaking, really, really young material. We're only, talking about 125,000 years ago. And so there hasn't been a significant amount of subsidence, maybe a little bit, but not a huge amount of subsidence, certainly not any uplift, no plate tectonics going on of note over that time scale. And so you're really getting a decent estimate, at least, sort of back of the envelope estimate of sea level just by walking up to these outcrops, right? And so the simple fact that you can walk up to these beds of shells in the intercoastal and there's just shells falling out of that sediment tells you that the ocean used to be much, much higher, right? The beach is now a couple miles to the east of where I'm standing here. And so I went down there with a group of students. We collected a variety of species. That is a Mercenaria. A student named Jade is holding there. And some of these ancient versions of Mercenaria, which of course there's many Mercenaria around now, but they don't wash up on shore. The modern ones don't wash up on shore as the size that you see in the fossil record. The ancient ones, when no one was harvesting them for any reason, can be sort of softball size, which makes them easy to find for sure. And so we collected those and many other species, had students sort of sifting through these shells, and you can see some of that work there, sort of the initial organization work here. So what we're doing with that material is thinking about the perfect samples to sort of represent different parts of the last interglacial, and also starting to build a larger data set across the uh, entire Atlantic coast. And this was kind of the first site that we worked on to do that. And in addition to fossils being readily available and dated in that location, we also were interested in studying this exact spot because it is just south of where today we have this major transition from warm to cold water in the western North Atlantic. The Gulf Stream, I'm sure virtually everyone listening to this is familiar, but the Gulf Stream brings warm water north and then takes this right turn at Cape Hatteras, more or less, and then starts moving towards, say, Iceland. And so we were interested in collecting as many sites in that sort of area as we could. I will note there is a gap here in in the greater Maryland region. To my knowledge, there's not a lot of last interglacial material available, at least that you can walk up to, but I'd be happy to hear otherwise if anyone knows anything about that. This one dot up here is the Sankaty Sand out on Nantucket Island, which I did not go sample myself, but other people in our group went and did. Um, and so we're kind of building this record similar to the pile of shells that I just showed you from these different sites. And in some cases, these are old pit collections. So they're, excavation pits, quarries, and so on that no longer exist or at least are flooded. We've been doing a lot of this work in collaboration with John Waymiller, which maybe someone here is familiar with at the University of Delaware or emeritus at the University of Delaware, who's also been really interested in dating a lot of this material. So he's been doing a lot of the work on actually figuring out that these are last interglacial or not. And so what do we do with those shells? I'm kind of dancing around it. What we do is we select the best ones for a variety of reasons. It's very strange that this figure no longer looks good. But anyway, what we do is we take these shells. I'm going to see if I can, guess there's nothing to be done. At any rate, oops, we take these shells, we sample along them. So you can see that there's lots of little pits taken across this Mercenaria shell here. And so what we're doing is we're basically examining these as though they're tree rings. Maybe you've heard of dendrochronology. So dendrochronology is the study of tree rings. You can look at the widths of those tree rings, and folks also look at the geochemistry of those tree rings, right? And those that can tell them about droughts, it can tell them about growth rate, it can tell you even about temperature when you're talking about trees. Turns out clams and a lot of other hard mollusks will also give you that same type of information. Many clams will live several in cold weather climates, sometimes hundreds of years. And so across a given shell, you can actually get seasonal records. And again, I have no idea why this is blurred out. That's completely bizarre to me, but at least you can see roughly that there is an up and down sawtooth pattern here. And that's really all you needed to take from it anyway. This up and down sawtooth pattern is temperature going up and down over the life of this shell. So what we're able to do with the isotopic geochemistry of a shell is we take that, we take these little samples across it, and we reconstruct summer and winter temperatures for, in this case, 125,000 years ago. So it's this little 4-year snapshot of summers and winters a long, 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 long time ago, which I think is pretty cool. It's a very high resolution climate record. And so if you take multiple shells, you can start to do some actual statistics on what were summer temperatures at a given time, what were winter temperatures at a given time. And so, and I should also mention, here's Alex, great picture of Alex on a boat. We of course did need a boat at some point to get some of these outcrops, and we rented a pontoon at a normal tourist pontoon rental place down there in Myrtle Beach. And the person renting it, of course, gave us lots of tips on like where the best drinking islands were, essentially. And we said, no, we're going the other way. We're going up the mucky part of the intercoastal. We're gonna go get dirty. See you later. Oh, I see there's the chat is open here. There's some questions here. Uh, I'll read them out loud. How well known is the oxygen isotopic composition of ancient seawater, and how does it influence the reconstruction of paleoclimates? That's a great question. I would argue it's less well known than people say it is. And so a big reason why we use this clumped isotope technique, which is again, sort of a more modern, it was developed 2006. The reason we use this clumped isotope approach is it actually gives us that independent measure that we don't have to assume what the water it was growing in actually was. And this related question, how much deviation from the expected equilibrium fractionation between ancient seawater and fossil shells and non-equilibrium fractionation affect these things? Yeah, so non-equilibrium fractionation is always something we have to think about. Species-specific effects are something we have to think about. It turns out that most mollusks cooperate pretty well is the short answer to this, right? So most mollusks in modern studies, done some modern work myself where we're measuring just living shells right now and kind of checking whether they actually give us the right answer. The answer to that usually is yes. And in the cases where it's been no, we just kind of don't use those species. And usually it's because they're growing too fast. So a juvenile oyster, for example, a very young oyster, will grow a shell so fast that it's not in isotopic equilibrium with the seawater, and so it'll give you sort of an incorrect answer on what the temperature it was growing in, for example. So the answer is, yeah, these are concerns we have to think about, but they have more or less been accounted for in what I'm showing you here. So what are the results from this project of the East Coast? Cutting to the chase. Here they are, more or less. So what are we looking at here? On the left, we've got uh, just the locations where we've actually got shell data from. And then on the right, we've got the beginnings of what those data actually look like. So latitude is the y-axis on this graph. Temperature is the x-axis on this graph. So warmer is to the right. And then all those funny lines that are in the background, that is actually showing you monthly average temperatures up and down the East Coast for the actual water right off the coast. So we're looking at a subset of the data here. We actually have a little bit more data than this, but it's not in as nice of a figure, so you're getting this version. At any rate, what we've got is the Sankati sand samples up here at the top look very warm relative to today. Basically, we have summer conditions that are warmer than summers today, and winter conditions that are much, much warmer than winters in the past. Or sorry, than winters today. Uh, the Myrtle Beach group, this middle one, basically gives us something somewhat analogous to today, but maybe slightly colder on average, and indeed has winters that are colder than winters are now. And then lastly, we have some similar records from Florida that are strikingly cold. So what these data are showing us, if we just take them directly at face value, is that we've got warm temperatures in the north. We've got like modern temperatures sort of in the mid-Atlantic, and we've got much colder temperatures to the south. In other words, that there's not actually a lot of a latitudinal gradient here. Um, and these Florida data, I'll tell you, have warmed up a little bit as we've actually run more samples, so they're not quite as extreme as what I'm showing you here, but they're still certainly colder than modern. And so what we're basically saying here is that if you go to the beach in the middle of the last interglacial, it wouldn't actually be that different of experience if you're at the Jersey Shore versus the beach in Miami in terms of average annual temperature. And that has to do, we think, with the way ocean currents were organized in the last interglacial, basically delivering lots of extra heat to the poles and driving a strong degree of Arctic or polar amplification. So making the poles much warmer than today, while the tropics sort of had their energy taken from them. The energy was being delivered to the poles at a faster rate than it does in modern climate. Um, but those temperatures in the south were strikingly cold. And so the sort of next thing to test was say, well, let's take a look at the Bahamas because the Bahamas have been, for whatever reason, stricken from this map. But the Bahamas just sit right off to the right of Florida down there. And so there were well-dated last interglacial outcrops in the Bahamas, and so that's the next part of what I'll talk about here. So here we are. We're on San Salvador. There's a wonderful research station there. Maybe somebody here has been there. It's pretty famous among people that are into that sort of thing. Uh, and the one time I was down there, and I'm actually taking a class down there this spring break, this coming spring break. The one time I was down there, though, we were looking at these last interglacial deposits on the island of San Salvador, and also doing some collaboration with a few other folks, including Al Curran, who's been working down there a long time. This guy here is John Milroy, who wrote the book on caves in the Bahamas, and here is holding a machete for scale. I don't usually travel with a machete, but it turns out it comes in handy in the Bahamas sometimes. At any rate, what we were looking at here and why we're here, our excuse for going to the Bahamas for science reasons, was that these are some extraordinarily well preserved fossil outcrops. So what we're looking at here is actually two layers. And these two layers, which are part of what's called the Coburn Town Fossil Reef, that is how you pronounce that, Coburn Town. Coburn Town Fossil Reef preserves a distinct set of fossil corals and shells that are embedded within them that are 123,000 years old. And that date has really been refined very well, not by me, but by other folks who do uranium thorium dating. And then they've dated this layer of coral and other fossil material above to 119,000 years ago. And so there is a meaningful, significant, roughly 4,000 year difference between these two layers in the last interglacial. So our thought was we can, one, just examine in general what the climate is like in the Bahamas during the last interglacial. Look, does this really cold signal in Florida show up again, in other words? And two, can we find any differences over time? And so to do that, what we're doing is looking at uh, not the coral themselves. The geochemistry of corals turn out to not be a very good resource to preserve geochemistry over time because they're so porous. They allow more crystallization and sort of water dissolution to get in there. So in a lot of cases, they're not the ideal proxy material, we would call it, to actually measure climate in the past. So instead, we're still focused on things like bivalves. There's that glycymeris sticking out of the pretty hard beach rock there. And just extraordinary preservation at this site. You can see the pink coloration of that shell, pretty much like it just washed up on the beach yesterday, but is firmly lodged in 124,000-year-old rock. And so to make a longer, more complex story short, we measured from a variety of sites, actually on two islands. So San Salvador is this island right in the middle of the Bahamas in the far east. And then Great Inagua, I didn't actually travel to myself, but we had collections from there. as well in the far south. And we compared, at the end of the day, 6 sites, well, 5 sites for climate against each other to examine this, to try to examine this change over time and just see what the last interglacial climate was like. And so this was just published like this week, essentially. It was finally all done and dusted. And this is the kind of final result from that. So what you're looking at here is a simple box plot. And by that, I just mean there's really only one axis on this graph, temperature. So temperature is the y-axis. And then each of these boxes represents all the data from each site. So we're really just summarizing everything here. The reef 1 record here, that is the older reef. So that is the lower reef that's about 4,000 years older than the other 3 data points here. I'll address this purple one in a moment, but for now, let's just set it aside. So the red box, in other words, is earlier in the last interglacial than the other 3 sites. Then we have the modern range. So that is this gray box here. That gray box then shows us essentially the average conditions in San Salvador and the Bahamas today. And there is a very small climate difference between these islands, right? When we're starting to talk about the tropics, 500 kilometers of latitude doesn't matter too much, but San Salvador is slightly cooler than Great Anagua by a degree or two. And so at the end of the day, what we have is a lot of boxes that are lower than that gray bar. And so that's telling us once again that we have cooler tropical conditions in the Bahamas during the last interglacial, during this globally warmer interval. But that's less true of this red box to the left. So the earlier last interglacial time record seems to be still cool, but meaningfully warmer than the other data. In other words, we may have evidence here for a cooling trend across the last interglacial interval. I bring that up because it's actually an important point. The work that's sort of been done on the last interglacial so far, and really interglacial intervals in general, often thinks of these as individual time slices, right? It is the last interglacial climate, period. And those individual time slices may not actually be unchanging over that time, right? As you go farther back into geologic time, it gets harder and harder to resolve 10,000 year differences or even 100,000 year differences. But for the last interglacial, it's still recent enough that we can, in these specific, well-preserved, really well-studied locations, actually start to tease out differences across this geologically brief interval. And now I know 10,000 years to you and me is of course not brief, but geologically speaking, it is short. It's hard to actually figure out which thing happened first or exactly what age things are. And so it's only in these somewhat unique cases where we can see that. And in those cases, we seem to find a meaningful change over time. And that has big implications for how we think about the last interglacial. As people say, it's the last time it was warm. Well, the first response might actually be which part of the last interglacial we were talking about. Because we're talking about the later half of it. We're actually talking about a world. What these data show is we're talking about a world that is meaningfully cooler than today, at least in a lot of places, but where sea levels are also much, much higher than today, which is, it is, I don't know, initially surprising, I think, to think that that was actually the case. So if we expand that, we zoom out and we put this Bahamas record in a little more context. We had some data from 2 islands. The red boxes on the right of this figure I'm showing you here are modern temperatures today. The x-axis is now temperature, and the y-axis here is latitude. So up on this box is towards the North Pole. And what I've placed on here is a new island that we haven't talked much about yet, Bermuda. And so I'm going to zoom in on what the heck these data are in a moment. But all I wanted to sort of set the stage with those data is that today there is certainly a cooling trend as you go north, right? These red boxes move to the left as you go up. That is just simply because temperatures change as you go north. In the last interglacial, we seem to have 2 distinct climate states. We seem to have a interval where we have very cold temperatures, and that is late in the last interglacial, here labeled MIS 5E, Marine Isotope Stage 5E. I know that's confusing, but it's just the last interglacial. So those gray points are giving us the end of that interval, the later part of it, and then the black points are earlier in it. And so there's really a distinction here. If we're looking at the earlier part of last interglacial, things are much warmer than later. And so that, of course, leads into Bermuda, where we actually have quite a bit more data, some of which is still coming out, and where we can examine this idea of cooling over time even more carefully. Before I get into that, I kind of actually have to start at the beginning again. Um, so Bermuda is the place where this whole sort of part of my career kind of started. As I mentioned, it was a side project as part of my PhD. And I'll tell you why that was. So a lot of my PhD was working on dolomite, which is a sort of enigmatic carbonate mineral that we only kind of understand how it forms. I'm still interested in that, but I also wanted to do something else. And my office mate, when I was a PhD student, a guy by the name of Will DeFleece, he's a professor in Australia now, uh, developed a project to go look at cements. So basically new precipitates of carbonate within rocks, within carbonate rocks in Bermuda. And he went there, collected a bunch of stuff, including some fossil shells, came back. This is a picture of Bermuda, of course. And what he found, actually what an undergraduate student found in analyzing those shells, was that they kept coming up with really cold temperatures. And these were all shells from the warm last interglacial. So it was kind of strange that we were getting cold results. And it was sort of like, well, maybe the undergrad messed it up somehow. But it's good enough justification that I wrote a small grant and put together a trip with my girlfriend at the time, now wife, as my field assistant, and we went to Bermuda and said it was for science reasons, and it at least sort of was. But it turned out that sort of side project turned out as something that led to pretty much everything else in this talk. So why would you actually study Bermuda climate? Let's start there. What did I put in that small grant in 2014 or so? Uh, Basically, it sits in the Atlantic Ocean in a point where the Gulf Stream makes a big difference. So the Gulf Stream is making that turn at Cape Hatteras off to the right, off towards the east. And Bermuda sits at the place where it gets a lot of that warmth from the Gulf Stream. It gets these eddies that come off the Gulf Stream and keep it warm. For that reason, it has the farthest north coral reefs in the Atlantic. Um, it's sort of almost artificially warmer than it would be otherwise because of that current. And so the basic idea was, hey, if we can study climate at Bermuda, we can actually say something about ocean circulation in the past, because what the Gulf Stream does has a big effect on local climate. And the initial way we did this, we actually did it twice for reasons I won't go into today, but we did it a first time and then followed up on it with some other results, was with these big guys, Ceterium pica. These are pretty cool critters. That picture on the left are modern living snails. So these are marine snails. They kind of live in tidal pools and then they go offshore and they hang out on land even a little bit. They're huge. They can be, I already used the softball as a scale, but I'm going to use it again. They are about softball sized. And if you cut these guys open, not when they're alive, but you find a shell that it's no longer occupied, you once again see those sort of tree rings within them. And so just like a clam, these things will record changing geochemistry over time. And so we did a lot of high resolution work looking at the seasonality or the sort of summer and winter conditions as these guys were growing in the past. And Jade Zhang there in the bottom right, she helped with a lot of this work, especially the second round of this work and as part of her PhD. And to cut to the chase here, we did indeed find really cold temperatures. So this graph is showing you temperature on the x-axis, and it's showing a quantity I haven't talked about very much, and I'm still not going to talk too much about, but I'm showing it to you, which is seawater 18O. This is the oxygen isotopic composition of seawater. When we measure the actual temperature of formation of a carbonate, we can also calculate the chemistry of the water that it formed from. And so that's what the y-axis is here. And especially at one particular site. So we measured really a lot of shells from two sites, and one of those sites came up with very, very cold temperatures. And to sort of prove that this basic approach works, we also measured two modern shells. These black squares are just modern, very recently alive Cetarium pica, and they overlap more or less with modern conditions, right? They maybe even are slightly warm biased, which uh, you know, if our conclusion is things were pretty cold, then you don't really mind a warm bias in your record. So we found this cold record. And we had a pretty hard time explaining what it was. And we finally decided on something a little bit splashy that I will say right now I don't fully believe anymore, which was this. Meltwater pulse recorded in last interglacial mollusk shells from Bermuda. Basically, we said we don't know how to explain these really cold temperatures. Our best idea is what we know does happen is when an ice sheet melts, including the Greenland ice sheet, there will be these pulses of melting that occur very quickly over hours to days that put dramatic amounts of fresh, cold water into the North Atlantic. We do know these happen. They're called Heinrich events. Um, we posed, hey, maybe we found one of these during the last interglacial, as opposed to when most of these have been described from, which is the last deglaciation, more like 18,000 years ago to 10,000 years ago. So this was kind of a provocative idea. And the mystery sort of remained, okay, maybe, but why are these temperatures so cold? This interval is supposed to be warm. Did we really record something like this, or is something else going on? So the only answer I had for that was, well, we just need more data, right? And so the next step here was to examine a completely different species in a completely different location on the island. This was an undergraduate project at Grand Valley where we looked at oysters. So we had this pretty cool collection. I'll come back to this slide, I promise. But we had this pretty cool collection of oysters from a different site. This map is showing a few sites here. My laser pointer out again. So Bird Island and Verrill Island are where I'm showing you new data from now, or I'm going to describe new data from. Rocky Bay and Great Bay are where the older, especially Great Bay, were the cold data from before. So nothing on Bermuda is very far apart, right? It's an island that you only drive scooters on. It's nothing's too far from anything else. We're talking about 5 kilometers apart that these sites are. Um, But also importantly, this oyster bed, which is I'm showing you in the top left and some of it in the bottom right here, this oyster bed is exactly at sea level. In fact, it's actually a little bit below high tide. You can see the high tide line here. You can only sample it at low tide. And so it really is, you know, some of the probably either first or last, but we think first material put onto the island as sea levels rose during the last interglacial. In other words, we thought that these data might be a little earlier than the other data I talked to you about. And we did the same approach. We took these subsamples across the shell and reconstructed seasonality from individual oyster shells. And what do those data look like? They look like this. Every single dot here is an isotopic measurement. I'm not going to get into the nuance of exactly what the colors mean here because they don't matter that much. The key takeaway here is that the temperature range, the overall temperature range we get, is more or less exactly the modern temperature range. So on its own, this is a not very exciting result. We picked up some old oysters from last interglacial and we said, we found modern temperatures in those oysters, right? Bermuda in the last interglacial was basically the same as today. So by itself, if that was the only study we did, we'd kind of say, well, here's our results, so it goes. Last interglacial was kind of warm, just like now. But since we have more context, we had these very cold data from another site, the question then became, well, now what's going on? So we can't seem to find these cold temperatures anywhere else. And so the answer beyond this was published in 2024, was then, okay, well, we better just keep measuring more. We'll just keep throwing more data at the problem until it is solved. And I'm going to, in my last few minutes here, I'm going to argue that that has actually solved it. So that, you know, we've gotten to the point now where we're going beyond what's actually published. This is sort of new, hot off the presses stuff. So we had done a lot of collection. We did some more collection, all under permit for the record. It's actually the folks at Bermuda at the Natural History Survey there are super, super great to work with. Um, did a lot more sampling, did some stratigraphic sampling, took different species again. So we'd measured these giant snails, we'd measured oysters. Now we're going to measure sort of more normal clams, things like Lucina and Glycymeris, across even more sites and use different species at the sites we've already measured. Questions like, are those cold temperatures a fluke or are they real? Are addressed by these data. And the other question we're addressing with these data is there some highly local thing that's affecting climate, right? Are those oysters warm because they're sort of in a restricted warm pocket of water, like a lagoon, as opposed to, some deeper water offshore or something like that? And so the way to really answer that question is just more species, more data, more sites. And so we did that work. Again, here's a nice shell bed sort of sticking out. These shell beds, we think they're mostly storm deposits. So you kind of get fine-grained sediments for quite a while, and then perhaps an individual hurricane basically throws a whole bunch of shells onto the beach that then get preserved by finer-grained sediment on top. And to bring this story towards the end, what we get is this record. So what I'm showing you here is temperature on a y-axis and then a whole bunch of different sites on the x-axis. So this is way more data than we've published from Bermuda before. The little numbers at the top are amino acid ratios. This is a method of relative dating. So it doesn't, unfortunately, it's not a way to put exact years on any of these things. We can't say like, oh, this is 126,000, but they can tell us which are older and younger than each other. And so what we see is more or less, yes, there are some caveats to that, but more or less, we have a lowering trend to the right. In other words, as we get closer and closer to modern, as we get closer and closer to the end of the last interglacial, temperatures get colder and colder and colder and start falling out of this blue box. And this, to sort of bring it back to the main motivation at the beginning, this whole box is what people call the last interglacial. This whole thing that you're looking at here is the time slice that people say, hey, it was warmer than today at this time. And what we're showing, or hope to show, is that, well, that is actually true for the beginning of the last interglacial, but as the last interglacial waned, temperatures started to go down. And so we end up with this. We have Bermuda data from basically the middle of this graph. This is showing you time, so 130,000 years ago on the right, 110,000 years ago, or closer to modern, closer to now on the left. So time is going to the left on this graph. And the thing I'll mostly point out here is the global sea level curve. So that is this gray line. So that is what we think sea level was doing relative to modern, which is at 0 right there. And so what we think happened to sea level in the last interglacial is that the Greenland ice sheet melted. And this is not my work, to be clear. Other sea level folks have done this work. But the Greenland ice sheet melted, and then later, the West Antarctic ice sheet finally went. And as that West Antarctic ice sheet finally sort of melted away, thousands of years after the start of the interglacial, that is also the time when temperatures were declining and declining and declining down towards the next ice age. And so again, we've now painted a picture of pretty clearly, I think, of a case where you have sea levels tens of feet higher than today, but temperatures that are actually falling over time. And to skip to the last of my summing up data points here, maybe to give this, just to end this on sort of a big idea, this might be sort of an analog for the distant future, right? When we talk about modern climate change, we're often talking about the next 100 years, projections of 2100. But if you project out climate change to, say, the year 3000, or maybe even the year 4000, you might be talking about a world where that warming has waned or at least stopped, and yet sea levels will still continue to rise. We've built enough heat energy into the system that ice sheets are going to slowly but surely melt away. Basically, a decent chunk of Greenland's ice and probably a decent chunk of Antarctica's ice is sort of doomed in a way. Maybe not on timescales that are relevant to you or I, but they are at some point going to sort of melt into the ocean. And so we are going to have sea levels come up someday, given that state. And this is definitely what happened during the last interglacial. So I'll leave it there. Thank you all for having me. This has been fun. There's my folks to thank.
Thank you so much. Does anyone have any questions?
I'll monitor the chat here too.
How did you get involved with this research?
Yeah, I mean, I told a tiny bit of the story there, but I was kind of interested in something beyond more there just like nitty-gritty geochemistry of carbonates and wanted to do something a
Mhm.
little bit more climate focused, and so kind of took it in that direction. A lot of my PhD was on this thing called clumped isotopes, and so especially when I was working on that 10, even 15 years ago, a lot of the action was, hey, we can measure whatever we want and finally get temperatures from the past that we couldn't get before. And so my thought at the time that I think is still right is really the first target should be the most recent warm interval because that's when you're going to have the best preserved records, right? And
Mm.
there were some efforts back then on like, the Silurian and things like that that are borne out to be, well, maybe they were altered or geochemically changed in some way since then.
So there's a question in the chat. It seems contractors that sea levels were high as global temperatures were falling. How much is the time between warming and response of large ice sheets?
Yeah. Yeah. So yes, it is contradictory for sure. Um, and to be clear, especially in the early part of the last interglacial, temperatures were definitely going up. So the sort of weird thing about studying a coastal last interglacial deposit, right? Something you can walk up to and grab the shells. By definition, you're studying something that was higher than modern sea level. And so the actual warming starts well before that, right? The interglacial period has to warm to get Greenland to start melting, to start raising the ocean. And so there's certainly warming going on that is then melting the ice sheet. And then that warming increases sea level for a while. And then as the uh, warming subsides, there's still sort of enough heat energy around that even though the climate is now starting to cool back down, it's still at a warm enough state that it can induce more melting. Um, and so you get a bit more ice to melt sort of on the way down before you sort of cross some threshold. The second part of that question, how much is the lag time between warming and response of large ice sheets? That's the trillion-dollar question, basically. Glacier folks that know much more about that than me are kind of studying that aggressively. Um, on the scale I'm talking about, it's centuries, but of course, there's nuance to that. We don't, I'm no expert in ice whatsoever, but um, questions remain about whether you can get rapid pulses of melting over decades and those sorts of things. So yeah, I think that's all I can say really about that.
Another question from the chat. Have you looked further inland in mid-Atlantic for samples to study?
Yes, to some degree, and have done some minor work on some of that stuff. As I bet some of you in here know, the farther inland you go, the older material gets, right? So if you want to go sample Cretaceous stuff, then you go quite a bit inland, right? Right along, like if I'm thinking North Carolina anyway, I'm thinking you go all the way in towards the Piedmont, and that's where the Cretaceous material sort of falls on top of the old coastline. And then the coastline sort of built its way out to the east. So in other words, from sort of the fall line, right, from where the Piedmont ends up and down the southeast coast, as you kind of go east, things get younger and younger. So if you want to study the last interglacial, you have to be very close to the ocean, very close to modern sea level, um, because sea level was, relatively speaking, not a huge amount higher.
Also from the chat, can you address what the reasons for the cooling were?
Yeah, the reasons for the cooling. So the the interglacial, so there were people around during the last interglacial. So Homo sapiens was around, but we as a species were not burning a lot of coal or gas at this time. We did not have SUVs and so on. So humans are not thought to have anything to do with the warming or the cooling at this time. Both the warming and the cooling is driven by orbital changes. So we get basically the Earth orbits the sun in a way around every so often that it gets a little bit more energy from the sun, get a little bit more direct energy from the sun, especially in the northern hemisphere. What glaciers really hate is hot summers. And so in the orbit sort of aligns itself in a way just by chance, by the sort of regular pace, it's going to get a little more energy in northern hemisphere summer, which starts to melt ice and sort of sets off a set of chain reactions that warm the planet further. And then eventually the Earth sort of moves into a different orbit where it's getting less energy in northern hemisphere summer. And then we start to just set off a set of climate feedbacks that cool the planet. We allow ice to grow a little bit more. We might actually slow ocean circulation a little bit, which then keeps more carbon dioxide in the ocean, which then makes the overall planet cooler, which can make more ice grow, can make the ocean slow down more, on and on. And eventually, between the last interglacial and now, you end up with a glacial interval. And so we can see this in I don't have a graph for you, but in the longer term climate records, they just go up and down and up and down and up and down and up and down. The phrase I've heard to explain that is super seasons. They're sort of like summer and winter, but they take place over 100,000 year time scales instead of every year.
How do you know ice melt didn't lower sea temps later rather than climate getting cooler? Sea temps near
Hmm.
the ice caps may or may not move the same as 35 north.
Yeah, sure. So it's complicated. And that would be one of the feedbacks. So melting ice absolutely cools the ocean. We see that right now. So we don't need to look at paleo records for that. If you look at temperatures in the North Atlantic today, there's sort of a blue blob just south of Greenland. And a decent re part of the reason for that blue blob is just the cold water that's coming off of Greenland every single day, cooling that part of the ocean. So that definitely has an effect. Whether it can affect climate as far south as something like Bermuda or the Bahamas, probably once in a while it does, but for really short periods of time, like weeks to months. So that's really hard to capture in a geologic record and really be confident that you did capture it.
Also from the chat, is there some sort of rise or fall in the land level as the ice melts due to the loss of miles thick glaciers?
Um, Let me think about that for a second. So that's a great point actually. So the reason that sea level in the past is really, really hard to study, and I'm really not a sea level person. But the sea level people will tell you that it's really complicated because the land moves, right? And also ice is really heavy. So anyone who's picked up a gallon of milk knows that ice is pretty heavy, or water at least is pretty heavy, right? And so you have a glacier, which can be miles thick, 10,000 feet thick. That's how thick we think some of the ice sheets were in North America. The one in Antarctica is on that scale today. That really pushes down on the crust a lot. If you then remove that ice, the crust kind of finally stretches back out, what we call isostatic rebound, and bounces back up. And so you can get, by that mechanism, you can get material that was below modern sea level, above modern sea level, even if it actually formed below modern sea level, and this all gets complicated very quickly. Um, and so the sea level folks do a lot of modeling work, basically. They take a lot of observations, they date all sorts of outcrops all over the world, but they also have to take into account these models of where ice was at different times and how much it pushed down on the crust and these sorts of things, especially if they're interested in local relative sea level as opposed to the entire globe average.
Did you see any diagenetic effects in shell samples?
Yeah, it's a great question. Yeah. And and probably every paper I've ever written, a reviewer will ask that question also. So it's fair. Yeah, so yes is the short answer. So we specifically try to target shells that aren't going to have those effects. The worst shells you can just visually see, hey, there's pits in it. You could see parts of it's dissolved or something like that. You know that's going to be a bad shell. One of the reasons we study shells at all instead of just chunks of limestone, right? Chunks of limestone are easier to find than well-preserved shells. But we don't study chunks of limestone to study ancient climate, generally speaking, because that sort of just bulk, muddy carbonate can very easily get altered. One of the main reasons we study a shell then is because that really dense calcium carbonate in the middle of a shell, here's my oyster, right? That that is just a pristine set of growth rings that have kind of been preserved from the outside world by the boundaries of that shell. So until we cut it open, it's kind of sealed in there, which is not true for just sort of bulk sediment. And even in this particular shell, we would definitely not sample the little pits that are in here or any in this area where you have sort of dissolution. There are other fancier things we can do. Look at the actual mineralogy under an XRD and other things like that. Um, but generally speaking, if it looks good, it is okay in most cases.
Thank you. Where is the data taking you in terms of the next project?
Yeah, I mean that's kind of the stuff I was showing at the very end. That sort of is the next project. So we're trying to kind of pull all this together, um, really document that cooling trend in Bermuda, and then also think about the East Coast stuff is not quite done either. So we're kind of bringing all that together. It ended up being more complicated than what I've shown here in that there's some material from a sort of intermediate stage, not the last interglacial, but another sort of warm blip, I would almost call it, something called marine isotope stage 5A. That's about 80,000 years ago when curiously there's basically some deposits above modern sea level here and there that sort of show up. So that would, I guess, maybe be one answer to your question. We're working on this warm blip, this 80,000 year episode that we've got some collections from sort of at the same time. I see that question. Why are some bivalves fluorescent on their internal face? Uh, Fluorescent, I'm not totally sure. The shell nacre or that sort of shine that you get, which is sort of analogous to how pearls form, it's really just pristine aragonite. And that pristine aragonite can get, which is just CaCO3, so it's calcium carbonate, can get tiny little, just like an emerald or a ruby or even a diamond, but to a lesser degree. Um, Tiny amounts of other stuff, a little bit of magnesium, a little bit of iron can actually give that a lot of color, right? An emerald only has its color because it has aluminum and iron in it, for example. So the same thing is sort of true of shell aragonite. Um, and that can also be part of the diagenetic question. If you have, well, if you see that in a fossil shell, you know you've got pretty good preservation.
Another question from the chat. Maryland does have lots of, plus, I'm going to mess up the word,
Yeah,
Pleistocene,
Pleistocene, yeah, yeah.
Pleistocene sediments. Much of it is fluvial. There is a paper about a marine fauna from Wales Bluff and Langley's Bluff along the Potomac River in Maryland. I think they were Sagamore stage.
Yeah, so Sagamon stage is sort of yet another name for Last Interglacial. So I'm interested in this. I'm writing these things down. If you want to reach out, I'm interested. Um, Langley's Bluff, Langley's Bluff. Yeah, I don't know anything about that, but I'm curious. We do sort of have a gap in the record between that one dot we have up in Massachusetts and the next farthest south one is in North Carolina. Or no, sorry, Virginia. Next farthest south one is in Virginia.
Hey, and I can send you that paper.
Yeah, cool.
I think it was published in the 50s though, so
Sure,
maybe
sure. Well, I'm
some more
familiar with
paper.
that sort of thing. Yeah. Yeah. Probably is a subdivision now or something, but be at least interested in looking at it.
Not a subdivision covered in riprap.
Mm. Sure. Yeah.
Even worse.
Yeah, even worse. Yeah.
Are you looking at studying other equatorial locations to see if the same sort of temperature things were happening in other parts of the globe?
Yeah, I mean, I think that would be sort of the next step to keep carrying this forward. I certainly haven't in particular. There's some records that are similar from the Azores, so on the other side of the Atlantic. Um, but not a lot of people have focused in so tightly on one period like this. A lot of this type of work has been more on sort of stabs in the dark. Well, I shouldn't say in the dark, but looking at wildly different intervals. So, you know, there's a pretty large shell chemistry project on the Cretaceous, in particular the what's it called? The inland seaway during the Cretaceous, right a lot of Nebraska and Colorado and Utah and so on is underwater during the Cretaceous. There's a lot of fossil shells people have been working on there. So in terms of last interglacial, I think I just showed you a lot of the data that's this type of approach. That very first figure I showed with many dots on it. Let me show that again, I think. This one. This is again mostly ocean core work. So that's about every ocean core that's ever been drilled. Currently, the ocean core program is on hold, we'll say. So that work is not happening right now.
Does anybody else have any additional questions? Or comments?
Thank you very much.
Yeah, you're welcome. Thanks for having me.
Yeah, thank you.
Seeing lots of thank yous in the chat.
Yeah, appreciate it. Yeah.
And I'm particularly thrilled that you have lots of undergraduate who are basically signing up for these classes.
Yeah, we're
It's
we're
cool.
doing reasonably healthy. Our enrollment, took a dive with everybody else's during COVID, but it's coming back up. We have about 70 geology majors at our school right now, which is not trivial.
Well, thank you very much for joining us this evening. That was a lot of information.
It was, yes. So whatever you got from it, I'm happy.